SIJP. Now, feature presentation will be by Mr. Tony Voellm, Senior Manager of Google, about their cloud performance. So please welcome Tony Voellm.
I'm known to speak fast. Konnichiwa. I'm going to speak it. I'm known to speak fast. If you want me to slow down, just ask me to slow down. Usually by the afternoon I've had at least 3 cups of coffee, a soda, and something else, so then I speak even faster. So if you give me in the morning, I would speak slowly for you, but in the afternoon it will be fast. So I'm Tony Voellm. I worked at Google 4.5 years. I have focused the whole time on Google Cloud, and from the beginning over here in Kirkland, we actually have about 500 to 600 cloud engineers in this area, working between Seattle and Kirkland, and total Google has about, I think, 2,000 engineers locally, working on just different various projects, including Kenji, who invited me here tonight, so thank you, Kenji, and Master, who helped coordinate everything, so thank you. So I'm going to take you through a very brief introduction to cloud. In fact, I'm going to teach you something about cloud you never knew, because I know everybody here knows everything about cloud. But I wanted to start by just reintroducing us to some of, sorry, I'm getting an echo out of the PC. I just want to reintroduce you to some of the concepts around cloud. So if you've never done anything with cloud, you'll have a good idea of what it is. For those of you that have done it a lot, you'll learn something new. And then I'm going to spend a lot of time talking about benchmarking cloud, like how we compare clouds and what we do to analyze it. And this will give you another set of insights into, how we go about trying to make cloud very, very fast, and how it's better than, far better than trying to do something in your own data center. I know I'm biased. Just remember that. So here is a very traditional view on cloud. And the traditional view on cloud is you'd oftentimes see a pyramid. And you'd see this pyramid that would be like infrastructure as a service, platform as a service, and software as a service. And this is the pyramid that a lot of times you would see. Here's a pivot of what this actually looks like from a practical developer standpoint. You have the infrastructure as a service. This is like, hey, I get a disk, I get a virtual machine, I get a database, I have some storage, some sort of object storage. These are fundamental building blocks. But what this also means at the infrastructure as a service layer is you manage everything. So this is, high flexibility, but also high complexity. And so if you think about, managing your own data center, or even trying to manage your, your home PC with a bunch of files, imagine doing this with hundreds of machines or hundreds of files and versions of software you have to install, and what operating systems are running, and how you maintain and manage this type of thing. And so infrastructure as a service is very popular, it's where a lot of us start. We typically move here first. But as you look at some of the new internet programming models with companies like Snapchat, they work more at a layer which is called platform as a service. And this is where they say, you know what, I don't want to manage things myself. I don't want to worry about OS versions. I just want to write my application, stick it into a set of infrastructure, and when more load comes in, scale it up for me. When load goes down, scale it down for me. Just manage the whole application, end to end. And so all you have to do is focus on your application. And this is really powerful. This is the platform as a service layer. And so here in the blue, you see it's talking about managing your application and your data. And so the first part over here is like, what do you do when you build an application? And so the things that you typically have to manage are applications, data, runtimes, operating systems, your servers. You have to worry about virtualization. If you're building your own data center, you typically turn on some sort of virtualization product like Hyper-V, which is a pretty awesome product by Microsoft. I worked on Hyper-V for 5 years from incubation out, so I'm also biased on that product. Storage and networking. And so, and if you follow the blue boxes across the different layers from infrastructure as a service to platform, the next piece I was going to talk about is the software as a service piece. And this is where you are now taking advantage of a set of services that some group has put together. It may be something like machine learning services. This is where somebody has written really complex algorithms to take apart speech and can take Japanese and translate it to English or English to Japanese or whatever it might be. And you as a developer, all you have to do is say, take this sound clip, pass it to the backend service, and it will tell you what it is in terms of text. And so the software as a service layer is really valuable because you get a lot out of it, but it is completely inflexible because it typically does that thing. So when you go from infrastructure as a service, very flexible but high complexity, software as a service is very inflexible and not very complex. And so it's also a very important building block. Here's a pivot on how Google looks at this. And so for Google, Google has taken this sort of traditional model and said, that doesn't necessarily fit with the way developers, build applications today. There's a whole sort of different view on top of this. And I was going to try to make sure this camera was there. Okay. And the way we sort of look at this is you have classes of things you're going to do. You have big data. You might have Internet of Things type applications where you're streaming massive amounts of data to a back end, and you want to figure out how you can mine this particular data. And so there's sets of services, on all different platforms, and Google is, I'm going to just talk about this one. Google has things like Google BigQuery or data pipelines that help you go and analyze the streaming data. But you might have, complex algorithms or something that you want to run, and so you have this compute tier. And compute is things like virtual machines, but it also has to do with like containers. And Google has this whole spectrum of, you can go from just managing, all the complexity yourself with a VM, all the way up to sort of containerizing your software and handing it off, to Google and say, you scale up and make more copies of this when I need them based on load that's coming outside, all the way to just moving this into something like App Engine. And so there's a spectrum in compute between everything yourself and everything managed, which is sort of this compute tier. Storage is really important overall to cloud. And there are many different storage offerings that you find. Typically, the most basic thing is a disk. It's like a persistent disk, and this goes hand in hand with a virtual machine. More commonly, though, you'll see things like Hadoop building on top of object stores. And object stores is just take this object, stick it in the cloud for me, and when I ask for that particular blob, it comes back. And there's all kinds of applications that have been built on this, including, yes, other disk technologies that you can actually mount inside your VM. And so storage has many different flavors, fast key value pair stores, databases, and so forth, and that all fits in the storage tier. And it will seem obvious when I say this, but nothing exists in cloud without a network, and so networks are really important, and they need to be fast and ubiquitous and everywhere. And so you can have this view on sort of the set of basic things that you need, storage, networking, compute, and data, and then you start to say, okay, well, what can I do with services? And then you have these software as a service tier pieces, like the AI models or genomics or things that can do things for you. And now what you do in modern applications is you take these pieces as you need them, and you put them together, and you can build really astounding applications. The example I used before was Snapchat, but there's many other examples. Coca-Cola and others have built campaigns where they create cool apps and they go out on the internet, and then you click oh, I love Coca-Cola, and all of these things run in cloud and do cool analytics together. However, here's the thing I know you didn't know about cloud. So I found this article a couple years ago, just as cloud was coming out, and it said, most Americans don't really understand cloud. And then they say, does it really matter? And then what was really fascinating about this article is it actually turned out that if you understood cloud, it was going to help your dating success in the world. And so what they found out was 17% of Americans lied on a first date that they knew what cloud computing was. But why did they care? I have no idea. So I know you didn't know that fact about cloud. So clearly cloud is good for your personal success. And the previous CEO of Google, I think, had it right, which is, I don't know what cloud is, but I do know one thing, it's a marketing term. So if you don't learn anything else about cloud, it's a marketing term. So with that, I'm going to move on and start to talk about what I do a little bit, which will give you context for the parts that follow around how we benchmark cloud. And by the way, if you have any comments or questions during the chat here, I'm fine to take them along, in line with the conversation. So, okay, so what do? Here's my job. My job is to create the most performant and most price performant cloud in the industry, period. And if you're from Azure or Amazon here, you should be worried because I'm very focused on this. And so what do I mean by most performant? And so there's many aspects to this. When you look at on-premises, hardware and infrastructure, one of the biggest concerns that comes when people move to cloud is like, why would I want to move to cloud? There are certain properties of cloud that are unique. One being the elasticity, the ability to get resources instantly. Everybody here, for 10 bucks, in less than 5 minutes can get a supercomputer. You could never do that before. This is what cloud allows you to do. Try to go do that through traditional procurement. It'll take you 6 months. You'll have to hire a power engineer. You'll have to hire all kinds of people to come in, lay flooring, and build a data center for you. It's quite complex. Cloud really literally changes the game here. So, we want the cloud to be this elastic thing. And so for performance, for my job is we look at how efficient is this, this sort of new paradigm. Do we get the right throughput? Are our networks fast? Is our storage fast? Do we get the right latency? Latency is very important. Most important thing in cloud is location, location, location. Are you close to the data centers that matter or close enough? This is very important. And so, we always look at things like placement, the efficiency, how efficient is my VM, and I'll actually show you the numbers here. And so there are a couple different things that I do to make cloud better. And it falls into these different buckets here. My team provides expert benchmarking. We go in, we work with customers, we analyze code, we really understand what's going on, and we make it better. We go in and we actually work with sales teams. I know, an engineering team that works with sales, we're kind of strange that way. But we also literally go into the product and change the product code at Google. And we're always trying to figure out how we drive those means of efficiency, throughput, latency, and so forth. We do events like this, community events, and with that, these are the products that we build. So what do we actually deliver? And you'll see this because you can take advantage of actually quite a few of the things that we do. We do competitive analysis reports internally, so if you ask me questions about cloud, I can answer them for many different clouds. We do product improvements, sort of this monitoring and looking in the infrastructure. We do regression analysis, and so when you're thinking about building on cloud, you want to really have the confidence that things work the way that you want. And so one of the things that we've done is we built open source tools that allow you to go in and performance analyze multiple different cloud providers, and I'll talk about that more. We've done blog posts where we go in and do things like, oh, look at this, Google Cloud Platform scales to 1 million queries per second instantaneously, which is completely unique in the industry, to go from absolutely no load on your service to handling 1 million QPS, which is astonishing. This is what cloud can do. Traditional hardware typically doesn't do this. And then we actually do quite a bit of training for my team as well, going around and working with different engineers and engineering groups. So benchmarking. This was the second topic of our meetup today. There's a couple ways to look at benchmarking. And so there's sort of 3 different patterns that you follow when you do benchmarking. And you'll see how I build this up to, what does this mean for cloud? And so one of the first ways of doing benchmarking is sort of this traditional mode of benchmarking where you go in and you write a set of code, and then you run it on a particular piece of hardware and you measure and you figure out what the result is. And what's cool about this graph is Drystone on the left is a very traditional type of benchmark. It's a CPU, instruction-oriented benchmark. It was built, almost back in the 1960s, I think was sort of the first incarnation of this. And one of the cool things that you see in this graph is how smart we all are as engineers. Because if you look at this bar, you see a very distinct line going up and to the right. And then every now and then you see these weird data points that like jump off the curve. And so every one of these data points, what they actually represent is a particular machine and a measurement of the Drystone benchmark on that machine. Can anybody here tell me why these points might jump off the curve? Sure. That's a great one. Yeah, maybe they spent a lot of money. That's a good one. Maybe they got the best supercomputer in the world and then ran it. That's one. How about another? They cheated! Yeah, guess what happens to benchmarks over time? We figure out how to optimize them. And so with these data points, people literally went in and figured out, okay, if I follow this exact path in terms of instructions, I can get twice the result, and so they cheat. Now you might think that that ended in the 1960s. Turns out it didn't. There was a phone manufacturer who got caught. Phone manufacturer won't be named, but there's a popular like Android benchmark on phones, and they were getting like, really amazing result nobody else could get. And what they found out is this phone was smart enough to recognize when you're running benchmarks, that if you were running a benchmark, it turned off all power management, sped up the CPUs as fast as they could run, which means your phone would last about 2 minutes at this power cycle before it turned off. And they got the best results in the industry. So even phones today have ways of optimizing performance. Well, as performance evolved, it moved on from things like just individual instruction counts where it wasn't that great, to more complex synthetic workloads where we tried to take multiple different types of code that users might be writing and running, and put that together into a different type of benchmark like LinPack, which is a scientific computing library benchmark. And here you can see the same sort of thing where you have this very distinct curve that sort of goes up and to the right, and I can't tell if these high dots over here are people figured out how to optimize LinPack, or Intel actually even at one time was literally embedding in their processors logic to detect if you were running a graphics code or something like that, and then it would just literally optimize that path. So this is a traditional way of doing it. You just run a benchmark. Another way of looking at performance is a methodology called like capture and playback. And this is where you take a code that the customer is running, and if it's a client-server application, sometimes you just capture all of the message requests that are coming in over the wire, and you log this out. And you log this out in great detail. You log exactly when the message was sent, you log the whole payload, and then what you can do later is, as a benchmark, you can play this back. And this has certain benefits and certain deficiencies. Some of the benefits is it's more representative, but where the deficiencies are things like the machine that actually generated these requests had a certain architecture, it had a certain memory hierarchy, and maybe this particular machine that was giving the request could only send that many. So maybe the problem wasn't even on the driving machine, or not on the back end, but on the driving machine. And so when you do these, capture and playback, you have to decide how realistic is it if I play back twice as fast? Is this benchmark still representative or not? And so as you're looking to adopt cloud, you're going to try these things. You're going to take some benchmarks, you're going to run them. You might capture your logs and try to replay them back. But one of the things you have to watch out for is, have you driven up the CPU utilization on the cloud to the same limits that you do on your local hardware? So that's technique number 2. Technique number 3 is, rather than run a benchmark, you just run your code. And so you're running your code over time, and what you do is you go into a monitoring cycle, and you monitor it. And you go look at how are the resources being used over time, how much CPU am I using, how much network, what latencies is my application experiencing, and Google Cloud and other cloud providers can literally provide this data to you real time in a console, and you can look at this. And then you even see really interesting things in here, which is, if you look at the cycles of applications by day, you can see this ebb and flow. In the US, the internet gets really busy around, 6 o'clock in the morning on, our time, which is like 9 o'clock on the East Coast, and sort of tapers off around 6 o'clock our time, 9 o'clock East Coast. And there are these rhythms that you literally see in usage on the internet. And every now and then you see a huge spike, and what you really hope is whatever your application is that you deployed suddenly became instantly famous and everyone's going to go home, super rich, right? That can happen too. So third technique is literally going and monitoring. So what do we do in terms of measuring cloud performance, and how do we do this fairly across different cloud providers? Well, one thing we did is we tried to come up with a really strict methodology. So my team handles a lot of performance reports, and so when you read the internet, the blogosphere, somebody will go out, they'll measure something, and they'll report, Google is the best cloud, and then the next day it'll be like Amazon's the best cloud, and the next day it'll be like Azure's the best cloud, and whatever cloud you want. DigitalOcean's the best cloud, and it goes on and on and on, and it goes back and forth, and it's really hard for us as developers to figure out, like, how's my application really going to work here, and how do I know what the truth is? Like, where's the truth? And so the thing that my team started doing about 2 years ago was saying, okay, we can either as a team go respond to every one of these new blog posts or whatever that comes out, or we can try to get ahead of this and set out with really proper methodology for measuring and analyzing and benchmarking cloud, and then we can go share that with everybody. And so the way we came up with this methodology, which is not new, by the way, if you go look at like X unit or J unit methodology for testing or whatever, this looks practically identical. What we're doing here is we're doing things like go set up the environment. And in cloud, this means go spin up your VM, allocate your databases, configure your network, turn on your firewall rules, whatever they happen to be. In the warm-up phase, this is a very classical benchmark stage where you go generate some load. And this is kind of interesting because you're warming up everything that's cold, and I'll tell you why that's interesting in a second. And then you have this phase where you execute. You just run the benchmark. It runs max speed. Then you're all done, you clean this up, and you publish your results somewhere. And so in classical benchmarking, what you typically focus on is step number 4. So if you look at something like an official TPCC result, which is a database result which measures database performance, what you do is you don't even look up at the ramp-up time, you don't look at the teardown time, you generate your load, you get to a really steady state, you take that value and you report that value as like, this is awesome. Now on cloud, remember one of the things I said that is a unique property is the elasticity of cloud. One of the benefits is you can spin up and tear down resources over time. And so you don't need to just go think statically of, I created these 5 machines, I'm running on these 5 machines forever. What you can do in cloud is say, well, I only need 1 machine right now, and maybe I need 3 at like noon, and then I need 2 at 5 o'clock, and by the time the day's over, I only need 1 again to do the work that I need to get done. And so the methodology that we came up with cloud is to say, you definitely have to include provisioning time. And so where the classical performance results that you report is only this steady state, if we're going to do something for our users in cloud, they also need to understand provisioning time. How long did it take them to get to that resource? So yes, you could do 1,000 transactions per second on your MySQL database, but if it took you 3 hours to set up the environment, that's not very cloud-like. But if it takes you 2 minutes and then you can get to this level and then tear down 2 minutes later, you can think of all new types of applications that might come out of this. So proper methodology was something we really focused on.
Question.
Sure.
Can I tell you the big difference between the kind of pre-execute and execute?
So pre-execute and post-execute are steps that are typically in there to go do extra data collection. So you're about to go into the execute phase. Pre-execute typically isn't the warm-up, you're not running the actual workload, but what you're doing is capturing a bunch of different diagnostic information, same thing with the post-execute, same thing, collecting diagnostic information. And so this is just a way of injecting or recognizing that you were classically only measuring in these 2 points in the loop. And yes, it does still matter what the steady state is, but including everything is sort of the different way to think about this. Does that answer the question? Okay.
Do you mean, is that for the measurement, or?
Yes, pre and post execute are really for the measurement.
Okay.
There might be something inconsequential that's in there, like I don't know, deleting a table or resetting a result or something like that. Classically you would never measure that. In the cloud benchmarks, we'd still include that. So even if you're doing some sort of extra configuration or extra cleanup, we'll include that. So our approach. Our approach is 2 things. One, this proper methodology. We have very rigid methodology on how we do things. And then we actually do all of the above. So instead of benchmarking cloud with one methodology, you're just running classical benchmarks or going in and running with sets of monitoring, or taking different sort of pivots on the data and so forth. We actually include all of the above. And so we have playback workloads, we have sort of monitoring type workloads, and we have classical benchmarks that exist because they still matter. Like the classical benchmarks do matter, but they matter in a different way. But other things that you have to think about when you look at cloud and you go benchmark cloud are things like geography matters. So I talked about location, that matters. It's important. Time of day really matters too. A lot of times, somebody will go out and say, okay, I'm going to go figure out if the cloud will work for my application in my company. I'm going to go measure it at midnight because that's what we do as computer scientists. We stay up all night and eat pizza and chocolate donuts apparently. And so I'm gonna do it at night, and you get this awesome measurement, like the internet is running at like, I don't know, 10 terabytes a second. And then you come in at like 9 o'clock and you tell your manager, it runs at 10 terabytes per second. And then they go measure it themselves and they're like, what did you do? It's running at, 100 megabits a second. And you're like, no, really, I got this measurement. Actually, it's just the cycle of the internet. And so as you look at the things that you're doing, be very cognizant of time of day. And so when you benchmark, this is something that we account for, and we do this by very detailed logging of how and when we do things. There's all kinds of effects that can happen in benchmarking. Go ahead.
Do you kind of take into consideration some kind of seasonal events rather than kind of daily kind of?
Yeah, I mean, daily events happen. If you look at like holiday events, and this is the thing, this is actually an interesting point about noisy neighbor. When you look at virtualization, a lot of times you'll have this impact of the busier the cloud is, the slower your workload runs, because you are running co-resident with other virtual machines. And the seasonality thing can happen, which is not everybody can get the resources they want around major holiday. And that definitely impacts it. Christmas in the U.S. is one. Rosh Hashanah might be one. In another location and so forth. And so, yes, it definitely matters.
Question?
Yeah.
So yeah, it is very interesting to think about what kind of things matters for the measurement result itself. But to do the right measurement, you need to create the right model that includes all the circadian rhythm or noisy neighborhood. So how do you come up with the right model to measure, and how do you decide which model is better than the other model?
Yeah, so the question is how do you come up with the right model, if time of day matters, and and how do you represent this? So I'll show you in a second how we've done it at Google. The way we do it at Google is we generate like 10 billion data points a month on performance analytics. And that's because we run continuously over time. Not everybody can do that. But we also, through our work with customers, we figured out how do the customers write the application, what is she or he doing, and actually trying to model the workloads after what the customers are doing and how they do it. And if their business, if they're coming in and saying, hey, we're going to deploy this application on Google, and we will make sure that we look at it over a 24-hour period. That's not Saturday and Sunday on the East Coast or overseas. And so typically on the West Coast for us, sometime between Tuesday and Thursday is typically a good day to look at some sort of performance benchmarking, because you're not in anybody's weekend typically in those days. And then looking at it over a 24-hour period, which means you typically have to go with a statistical modeling of performance in cloud. So with traditional benchmarking, I run it on my desk side workstation. It's going to be the same now as it is tomorrow and as the next day. In cloud, it doesn't work that way. Data that comes out of cloud, as measurements, tend to be very noisy, which is why like statisticians, statistical skills are really important. And when Kenji and I used to work together, I never made him endure this, but the performance teams that I now manage have, the last 2 years, gotten a holiday gift from me, which is a statistics book. I don't think they want any more statistics book. That turned out not to be as much fun as I thought it would be. But yeah, like statistical modeling is a really powerful tool in performance analysis. And I often joke, like the most important tool for any performance engineer or any of us measuring performance is a database and a spreadsheet. And the spreadsheet is so that you can graph and model what it is that you're looking at. And you'll see more of some of this measurement here in a minute. So what are the things that can go wrong with cloud? And what are some of these hidden variables? And so if you're trying to get to the right model, how do you get there? Part of getting to the right model is really understanding the cloud provider or the platform that you're working on. And each cloud provider has made different decisions that are both cool and non-obvious. They're cool because they're giving you benefits that you wouldn't ordinarily get, and they're non-obvious because they don't work like traditional machines. And so let me tell you a first example. So here, I'm giving an example of VM to VM performance. So in this particular benchmark, what we do is we take two virtual machines, each with 8 virtual CPUs, so in Google terminology, an N1 standard 8. We boot 2 of these in the same zone. This means they should be, within a proximity of some, sub-millisecond sort of, latency between each other. And then we run a throughput test between them. And so we run something like a net perf or iperf for a throughput measurement, and we blast bits from one to the other, and we see how fast it can get there. And here, what you see is, depending on the size of the machine, the little bars on the far left is an N1 standard 1. That means a 1 virtual CPU machine. Then a 2, a 4, an 8, a 16, and a 32. And what you see is this really interesting behavior, which is on a 1 CPU machine, you get basically 2 gigs of networking, which is phenomenal. Nobody else gives you this. And by the time you get to an N1 standard 8, you're getting almost 8+ gigabits a second. This is not obvious because the way networks work for us traditionally is I either have a 1 gig NIC or a 10 gig NIC. That's what I get. And so when you're used to this model of this very fixed amount of networking, and you move into the cloud world where the bigger the machine you have, the more networking you get, it changes how you have to think about loading and building your servers. And so this is one hidden variable, is how does the networking scale? And every provider has a different scale. Some decide if you have below 16 cores, you get 1 gigabit of networking. If you get 16 cores, you get 2 gigabits. And if you buy a machine that costs dozens of dollars an hour, you get full 10 gig networking. The Google model is, we just sort of like, hey, the more CPUs you have, the faster it goes. We up to a limit of like 2 gigabits per core, something like that. Now you can see we also have problems, which is we don't seem to scale at some point. And we're sort of hitting this 10 gig limit anyway, which is up here around 8 gigs, and so a 16 gig machine isn't quite as fast as the 32. Yeah, we have work to do, that's all I can say. It's still pretty awesomely fast, but it would be nice if it just like capped out exactly at 10 gigs, but it doesn't. So one thing you have to watch out for is, what's the network model you're working on? The second, this one is really kind of surprising, probably not to all of you, was surprising to me, is depending on what flavor of Linux you run or flavor of Windows you run, it impacts performance. And so here I'm showing you an analysis that we did, depending on the image that you use. We used Ubuntu, Debian, CentOS, CentOS 6, CentOS 7, and we literally compared the performance, and all we did was boot the VM with this particular image, run exactly the same benchmark, collect the results stochastically, right? We create hundreds of points for this particular bar. So we get really tight variance around this. And this is how it looked. And so if you go from like a Debian 7 image, Wheezy, all the way up to Ubuntu 14.04, you have this varying performance almost by like 20% change. And so this is a common thing that I've seen from customers, especially when they benchmark. They'll come in and say, hey, one cloud is faster than another cloud. Well, what image did you use? Oh, I used CentOS over here, but Ubuntu over there. And so this inconsistency leads to the misinterpretation of actually what you're going to get as a customer. You should run what you actually run. If you use Ubuntu, use Ubuntu. If you run CentOS, use CentOS.
Do you know why those differences come from?
Absolutely, yeah, I do. So the difference between these are CentOS 6 and 7 had different threading models for networking. One had this feature called MSIX and the other didn't. And so on 6, basically all networking interrupts would go to one CPU, and on 7 they can get distributed. But the reason why like CentOS 7 and Ubuntu are different is CentOS turns on the firewall by default for you, whereas Ubuntu turns it off. And what's interesting about cloud is every cloud provider provides a firewall outside of your virtual machine container. And so to have a firewall inside your VM when you've already gone to a firewall outside isn't that efficient, but CentOS hasn't actually ever turned it off. And so one of the things that I recommend customers do when they go and take an image like this one is turn off the firewall. And if you turn off the firewall, you'll instantly get like 10% better performance quickly. And when you go to Debian was the same thing, it was a different older kernel between like the Debian and the Ubuntu image. I've found the Ubuntu images, especially like 14.04 and beyond, to generally be the most efficient image for Linux, no matter what provider you use, Google or other. That tends to be the most optimized of them all.
Did you compare against Windows or against Linux?
Yeah, we do. So Google currently supports Windows 2008 R2 as another guest image. What's interesting is if you try to use some of the Linux performance tools like iPerf on Windows, They don't work. Windows, you have to go look at the Windows benchmarking tools, and so Windows has a tool called NTTTCP. Yes, 3 T's, not 1, not 2, but 3, NTTTCP to go benchmark. But it's kind of cheating, and I haven't really decided myself if running NTTTCP for benchmarking networking on Windows is equivalent to running something like netperf or iperf on Linux, and let me tell you why. In Windows, what this networking tool does is it actually issues 2 sends simultaneously. And so it's basically double buffering. It's sending 2 things in parallel, whereas this other tool only sends 1 thing and waits for a response, and then sends the next thing and waits for a response. Windows is like, send 2, I got 1 back, now send the next one. And so it's always keeping its queues full. I don't know, is that equivalent? It's hard to say. All I know is that when you're on Windows, you know, when you're in Rome, do like the Romans, and so when you're on Windows, run with the Windows benchmarking tools, and that is typically what we do, is look at like NTT, TCP, and compare it to, you know, the Linux iperf or netperf. Other hidden variables. Now this is really not obvious. I'm getting way out here in tech land. For all of you, you probably have no clue what I'm about to tell you, and if you do, I want to hire you, so just send me email later. It turns out when you're doing disk I/O, there are different disk queuing algorithms, and so most of us in computer science heard about the elevator algorithm, right? Like the classic disk, the head goes like this to the outside, you know, and like the disk is rotating really fast on the outside, and when you get to the inside, it looks like it's just going really slow, and you know. And so these algorithms that were developed classically don't necessarily work on cloud, because guess what? There is no disk. I hate to tell you that disk that you have in your VM is like a farm of disks out there somewhere in the infrastructure. It's usually thousands of disks servicing your imaginary one virtual piece of hardware. Turns out that the Linux algorithms of how you schedule IOs out to the disks, there's different ways that they do this. One is called CFQ, and this is basically a queuing algorithm, and it says bunch up a bunch of IOs before you send it to the disk. And it's trying to figure out exactly how long to wait before it sends them. There's another algorithm called no-op, which means as soon as I get an IO, give it to the disk. And this is actually interesting in cloud for scheduling IO. If you use no-op, you can clearly see it's a lot less variant and a lot more performant. And so I always say, why would you run a disk scheduling algorithm inside of a VM when there's going to be this host-side code that's also going to run a disk scheduling algorithm for you to actually persist your data? And so if you want to save cycles, turn off the disk scheduler inside the guest. And the way you do that is you go into you go down in the block device scheduler, and then you say NOP, and you turn it off. If you really want the details, you can email me. But this is another hidden variable, which is the way that the operating systems work can affect your performance. And so it's not just the image, but also the actual kernel of the operating system itself. Another one, zone matters. What's my time check, Kenchi, by the way?
45 more minutes.
Okay, fine. We're plenty of time.
Halfway.
Okay.
I didn't know.
Okay. So another one of these hidden variables is zones. So each cloud provider differentiates CPU architectures differently. Google differentiates its CPU architectures by the zone that you run in. And what I mean by CPU architecture is like Sandy Bridge, Ivy Bridge, and Haswell. If you have no idea what that is, it's slow, fast, and faster as CPUs. And so you want to run on Haswell CPUs because they are the fastest CPUs. The memory architecture is better. They have higher clock frequency. They burst better. They have all kinds of cool new instruction sets like AVX2 if you do scientific codes that the other ones don't have. Lots of benefits. And so one of the things that Google does is we do it by zone. So you might start up an N1 standard 8 VM in one zone, and then you run another, and you're like, why is the performance different? Is there a difference? Well, we solved this one by read the manual, and so we put the documentation out on the site, and we say if you run in this zone, it's this. Other vendors, I would say, have done something that's maybe a little more obvious, where they actually have different machine classes. And so, one might be a C3, 2 extra large on Amazon versus a C4, 2 extra large. And these are different architectures. And like an M3 2 extra large on Amazon is basically, I think, like a Sandy Bridge, whereas a C4 is a Haswell. And then you can just run these in any zone. So that's another hidden variable you have to worry about when you're benchmarking. Asymmetries. Turns out the internet is not symmetric. You know, I used to have this naive view of the world of the internet. I thought like when you sent data over the internet, it's like I go from point A to point B and it's just like this way and that way. Turns out that's actually not the case. If I send a packet from Washington, DC to San Francisco, it might go from DC up to like Toronto, over to Vancouver, and then down into Seattle. And then when it goes back, it might go down to LA, over to Texas, and back to Northern Virginia. And so the internet's not symmetric. So you think you send a packet and get a response. The send and receive actually come through different paths. And there's actually tools, like classical tools like traceroute, give you this illusion that they go the same way. If you use a modification to the tool called Paris traceroute, it'll actually show you both directions, the send and the receive. And it tries to figure out these paths for you. Also, it turns out the internet is like the wild, wild west of this thing called BGP protocol, Border Gateway Protocol, and the internet's always reconfiguring itself. So these routes that you think you have right now might change, and this is where one of the cyclical behaviors come from in performance analysis. For Google Cloud Platform, it turns out when you use VMs, they always get two internet addresses, two ways of addressing the machine. One is called an external IP address. This is like an internet addressable address. And then they get what's called an internal address. And this is a data center machine-specific address, like a 10-dot address. Depending on the address that you use for addressing VMs in Google, one is the, hey, I'm going to go out to the internet and back path, this, a slower path, and one is a very fast path, which is the internal IP. And so depending on where your VMs are and how they're communicating, you have to make decisions about which IP address to use. This is very true of all the different cloud providers. And then the same thing is symmetry, which is sending from zone A to B is not necessarily the same speed as sending from B to A. And so these are another one of these hidden variables that you have to deal with. And believe it or not, companies like Netflix have really sort of mastered this cloud environment, and they have lots of sophisticated monitoring tools, and they actually open source them. So if you haven't seen some of those tools, they're useful. Now, if you aren't already confused enough on how you're ever going to get a valid performance measurement for your application, I have just another couple interesting effects. Different providers have what are called burstable instance types, and they've done some cool things. They provide a really cheap VM for you, and it runs great for like a minute, and then it doesn't run great. And so what I'm showing you here is an example of some of these decisions you may not know. It's like, hey, I bought what I thought was a performant disk, and it runs great for a period of time, and after some period of time, it runs actually for what I paid for. And so what this is called bursting. And so in cloud environments, providers try to give you a good experience based on sort of standard workloads, and bursting is a really useful mechanism for disks where we could never sustain this amount of I/O if everybody did it, but we can do it for short periods of time, and then it goes down to a level that you actually paid for. But if you're not looking out for this, you don't know it's going to happen. You might size your deployment in cloud based on this burst area, like this particular graph right here, where you see, hey, I bought a 1 terabyte disk, which is guaranteed to run at 300 IOPS. This is actually a little older graph, it's faster now. Whereas if I get a smaller disk, which is a 250 gigabyte disk, it runs at the same level for about a half an hour, and then it drops down to a different level because you only paid for a certain amount of I/O or bandwidth. But the burst is useful. Now another example that's on this graph is networking. This is not something that Google does, but other cloud providers do, which is they'll let you run the internet, send traffic to the internet really fast for only about a minute, and then it drops down to like this really low rate of egress, what's called egress traffic. And so as you're looking at different cloud providers and trying to figure out measurement, sometimes you really do need to read the details, but if you run long enough, you can typically get to the steady state performance. It turned out Google was the first cloud provider to do this really unique and I think beneficial thing for disks, which is, but not intuitive, which is the bigger your disk, the faster it runs. Remember I said like the internet, like the bigger your instance type, the faster it is? But for disks, there's this trade-off of how many IOPS do you get, like how many sort of transactions for your database you could get per second, versus how fast could you write or read to the disk. And so IOPS and bandwidth are tied, and they're not tied to size. So traditionally, you buy a disk, it runs at one speed. You buy a SAN, and you expect SAN level performance. It runs, amazingly. It has all this cache. Now, disks in cloud providers tend to be this hybrid thing between like a classical disk and a SAN. And to adjust for this model of how do we determine how much performance to give the end user, we decided to base it on the size of disk. And so Google came out with this, so the bigger the disk, the faster it runs. Once you know this, it's easy to understand. Counterintuitive if you don't actually know it works this way. And then other cloud providers actually have also done the same thing, so it seems to be a pretty good model. Which is why in this particular graph, you see the 1 terabyte disk runs really fast, and then the 250 gigabyte disk runs at a quarter of the speed. It's because the bigger the disk, the faster it runs. But we are willing to let you burst up to a 1 terabyte speed for a period of time, and this helps install software and get through boot and a bunch of sort of mechanics you typically have to do. Now this is fascinating. Who here would think that the more of a CPU you use, the slower it goes? That sounds not quite right. Go ahead. You would take this, huh? Sorry.
No, yeah. Wait, you said the more of the CPU you use, the slower it goes.
That's right. So if you have a 32 CPU machine, if you use 16 CPUs, they run at one speed. If you use all 32 simultaneously, they run at a different speed.
Okay, in parallel. Yeah.
And so this graph here, what it's actually showing, and so if you look at the blue line, what this graph is actually showing you is a classic benchmark called spec CPU. It's still sort of the marquee benchmark for how you measure CPU performance. It has a bunch of different types of workloads it runs, scientific codes, video streaming, transcoding, so forth, all these different things that you do. And it puts these all together and it runs it and it gives you a score. And so here, what we're showing you is how utilized the CPU is. So if you're using basically one CPU on the machine, how fast can you expect it to run? And as you progressively use more and more of the CPU, you see the performance drop down and drop down and drop down. And so if the whole machine is used, it runs at half the speed of an unused machine, like basically the one CPU. And how this matters in cloud is because cloud is multi-tenant, meaning multiple things run on the same CPU. If your VM lands on a CPU and Kenji's VM lands on the same host CPU, if Kenji is idle, you're going to run really fast. If Kenji is trying to use all of the CPU that he's bought as well as you, aggregate, both of you may run a little bit slower. It's a really fascinating effect that happens in cloud. There's no way for you to control for this, really. I mean, what you'll see is basically maybe somewhat of a change of 5 to 10% in performance for this kind of behavior in cloud. But it's interesting to know if you ran right now and you run later, it might not be anything other than the CPU is running at a different clock frequency. And so at the root of this is how fast does the CPU run? Runs at a certain frequency. Intel has figured out that if we let certain CPUs run fast, it's beneficial. If we run them all run fast, the machine burns up. So once everything is engaged, they have to run everybody a little bit slower so that they keep a consistent power envelope and you don't let the blue smoke out. That's what we always joke, right? Like, if you've ever worked in a kernel team, you probably burned up at least one machine, because literally you can set the CPU so that they run so fast, and after a while you just see it go like that. That's bad. So what have we done for the industry to help you do this? How do you tackle this? So everything I talked about before, we have put together in 2 tools, both in open source on GitHub. You're totally open, downloadable. One tool is called PerfKitBenchmarker. This is the benchmarking tool where you've taken these different types of workloads I talked about earlier, put them into a single, very easy to run benchmarking tool. We worked with Microsoft, with MIT, Stanford, EPFL. We worked with Rackspace, CenturyLink. We worked with over 33 different entities in the industry to create something that we felt was fair. And we put it out in open source, so you can go look at the methodology yourself. If you think something is measured incorrectly, let us know, we'll change it. If you think something is missing, we'll add it. And we continue to get lots of engagement. There's like 470 stars on GitHub, so if you like a project on GitHub, you click a star, you fork it. There's like 470 stars and, I don't know, 80 forks or whatever the heck it is, which is a huge amount of engagement, especially for a benchmarking tool. It's the third most popular Google Cloud open source project we have out of like 412. You know, number 3 wouldn't have sounded great if I said, yeah, it's number 3 out of 3, but no, it's actually number 3 out of like 400 plus. And the community around it continues to grow. One of the reasons why people like this tool is the ease of use, and I'll show you an example of how you actually run it here, and you'll be astounded. The second tool that we did is, nobody likes to look at like tables and charts of data that comes out, and so we put out a dashboarding tool called PerfKit Explorer, also completely open source. It's a complete analytics dashboard. You can make it pretty much run on any data source, although the version we have on GitHub actually works with a tool called BigQuery, which I'll tell you about in a second. So when you want to go benchmark cloud, we've given you a benchmarking tool and an analytics tool to go look at your data, and you can go put millions and millions of samples into the back end and actually go analyze them later. So what does the PerfKitBenchmarker look like? It was built for developers, with developers in mind, and we did a couple of hopefully smart things. We separated out the different stages of how benchmarks run, and so you remember I talked about, hey, this provisioning stage is really important, you want to collect and measure it. We have provisioning separated out, and we do, for every benchmark that runs, collect the full end-to-end time. From the time nothing existed in cloud, till the time you could actually get in and run your benchmark, to the time it took to shut everything down. So we include all the startup time, all the shutdown time, and the full end-to-end time in terms of the benchmark. Super cool. We put down an execution phase, and we put 3 phases in execution: prepare, run, and clean up. And so as a developer, sometimes you want to run experiments. And so with the benchmarking tool, you can say, hey, benchmarking tool, prepare the environment. And so if you're running on Google Cloud Platform, or Amazon, or Azure, or DigitalOcean, and pretty soon Rackspace, you just say, set this whole benchmark up. It literally goes out, provisions the machines, installs all the software, configures everything, and stops. And then you as a developer can go in and sort of tweak things if you're trying to figure out, you know, how to make this look like more like your environment. And then you tell it to run, and you can tell it to run again, and run again, and run again. And then when you're all done, you can say clean up, and it will tear everything down. And my suggestion is check twice, because man, if you leave something running on cloud, it can get expensive. Then it goes through, unless it's Google Cloud, then it's really cheap. Scoring, we go in. We don't really have a scoring module today. I've actually been asking academia how we combine a set of scores in the benchmarking. If you have some really unique ideas, or you think you have a good way of how you combine a set of different types of data into a single value that would let us compare across platforms, let me know. We didn't have a great way to do it yet. I thought it would be a great, you know, sort of PhD or dissertation topic, and then somebody there can go tackle it. And then we have the reporting tools, and so the benchmarker understands the Explorer tool, and it will publish the data out to BigQuery, and then you can just graph it inside the tool. What benchmarks do we have? We actually have quite a few. So NoSQL is very popular in the industry in terms of building, you know, internet applications, and so we have a good representation there. We have Aerospike, Cassandra, MongoDB. Pretty soon we'll put Couchbase in here. For HPCC, because actually a fair amount of scientific computing is done, and it's done, you know, multi-cluster. HPCC is a scientific computing benchmark. It includes Stream and a benchmark called HPL, which does like a parallel impact. We include things like, you know, the basics, CoreMark for CPU. We include FIO for looking at like just disk benchmarking. We look at object store. If you want to know whose object storage is faster, is it Amazon, you know, Google or Microsoft, or, you know, DigitalOcean or whoever. DigitalOcean doesn't have an object store, so they're going to be the slowest. But if if somebody has an object store, how fast is it? You can find out. And then we have something that we did, which is we put out one benchmark of our own. And so what we haven't done to date is created our own benchmarks. We actually created a benchmark with Stanford. There was a PhD student who was trying to look at data center power management and efficiency. And what this graduate student did was to create a benchmark called OldieSyn. And this is online data intensive workload. But really what it is is a fan-out workload that represents web search. And so the way web search typically works is a request comes into a head node, a virtual machine, fans it out to multiple other machines, which fans it out to further other machines. They all do some computation to find out whatever your answer is, and they aggregate this result back up, and out comes your answer. And so OldieSim is a benchmark that's there, and it actually is part of the benchmarking suite. How easy is this to run? It's this easy to run. You just do PerfKitBenchmarker.py, you know, your project, if it's project-based, Google, everything is project-based, other providers, not so much. What's my project? What cloud do I want to run on? -- cloud equals GCP. And then, you know, the benchmark you want to run. You can run one or all the benchmarks. If you don't specify a benchmark, it runs everything. If you specify a specific one, it runs that one. And of course, there are a zillion command line options that you can tune or configure a benchmark if you want to. One of the premises of the benchmarking tool is we run with the defaults. We don't change anything that isn't the default. And the reason why we do this is we know that as developers, we don't have the time to go learn everything about everything. And typically when we use components, we just take the defaults. We install MySQL and that's it. I mean, somebody's probably not in there tuning the, you know, the InnoDB, you know, TX threads and RX threads. About the only thing we'll configure in something like MySQL is the buffer pool. How much memory should it use on the system, and that's it. And so the benchmarking tool follows that premise, which is cloud should be amazing just by default. If you want to run on Amazon, you just type cloud equals -AWS, and if you want to run on Azure, -- equals Azure, and if you want to run on DigitalOcean, -- equals DO, and you hit enter, and it takes care of everything for you, which is why the benchmarking suite is so powerful. One of the things that we did with the benchmarking tool that I think is unique is we make it run like the developer. And what I mean by this is, instead of using all the proprietary APIs to go manipulate resources that, you know, the providers give you, we use their command line tools. So on Google Cloud Platform, we use a G-Cloud tool, and literally we log everything as it's running. And so you could literally cut and paste and cut and paste, and you'll get exactly the same result as the benchmarker running. And so if you're trying to learn cloud, the benchmarker is really useful for that too, because you can figure out, oh, I had to configure a firewall, and this is how I do it. Oh, I had to create a disk, this is how I do it. And it does this across multiple different providers. And so it's really cool to sort of watch the different, you know, command line language that each of these providers have. And which, it makes it both hard and powerful at the same time. Some cloud providers like to make breaking changes in their command line tools, which is no fun because then we have to go update the benchmarker. But we declare like what versions of the tool it runs with, and then we roll forward with each iteration.
Okay.
Sure.
Did you write that part by yourself, or the vendor provided you the command line?
It depends on who it was. For Google Cloud, clearly we did that ourselves. Rackspace has built their own provider. They're really close to checking this into the main line. We're probably about a week out. Like they have a branch off of it, and you can see what they've done. They're really close to checking this in. For some others, you know, we did it as well. But we actually went and then worked with the provider and said, hey, is this the right way to set it up? Turns out, I think we probably got more bugs fixed in Azure than anybody else, because we kept coming back, hey, do you realize your command line tool, if you delete the network, you know, this deletes the network, it deletes all the networks? And they're like, oh, yeah, that probably is not that friendly. And so then they went and changed the tool so it doesn't do that anymore. So that wasn't my intention to make that better, but it actually made that better too. Yeah. But because it's open source, actually, if you go in and you look at the bugs, I really appreciate there was, I can't remember his name, there was one guy from Microsoft who opened like 20 bugs on the benchmarker, just helping us improve it, you know, for the environments, because we want it to be fair. And if it's not fair, I would rather Google look bad and it be fair than Google look good and it not be fair. And so one of the things we keep trying to do is saying to the vendors, hey, if something doesn't look right, help us fix it. Because we want it to be accurate and representative. So it's not easy to run. I'd run it here, except for running anything over the internet in a Wi-Fi room like this is perilous at best. But if you get me afterwards, I can run it for you. Sure.
So how do you see this project sort of expanding with all the companies that are contributing to it? Do they now use their own in-house tools, and how is that sort of thinking?
This is an interesting one. Clearly inside of Google, we use the benchmarker for a number of different uses. We use it to optimize our cloud. We use it to track, monitor, and analyze performance regressions. We use it to do competitive analysis. We use it to write reports. We use it actually as part of sales engagements. If customers are trying to figure out how to do something better, they can run the benchmarker and literally see this digest of the log message come out. I do know other cloud providers are actually using it the same exact way. It turned out we all built the same thing anyway. Why have everybody build the same thing? We all know exactly what we're all going to do. Why don't we just do it together, make it fair, and then we could just go along with this and not have to go duplicate effort across companies. This is like the second or third tool like this in my career I've built. And honestly, I was excited to open source this because then I never have to do this again. And especially the analytics tool I'm going to talk about next, because building performance monitoring dashboards and alerts and all kinds of cool stuff is really fun the first time. And it's maybe a little bit fun the second time. But by the time you hit the fourth time you're doing the same thing, you're like, geez, I just wish there was something in open source that would do this for me. And that's why we put that out there as well. So I expect it to be collaborative. The thing that I get really excited about is I actually see analysts, different analysts in the industry. 451 Research actually wrote a paper based on the benchmarker. I thought that was pretty cool. I would like to see companies like Gartner, as they write their Magic Quadrant report, to use something like this, because then we all have a very agreed upon, very transparent methodology as to how we measure things. I would find that very useful. Academia is really interested in writing more papers using this. What it turns out, as a PhD student, you don't have a lot of time, especially in computer science. You want to do something cool or new in operating systems. The last thing you want to have to do is go write a bunch of benchmarking goo and stuff. And so one of the cool things we did with the benchmarker is it will even run on a local machine. So if you say, hey benchmarker, I don't have a cloud, don't try to provision stuff, but here's the IP address of a machine. It could be a physical machine, non-physical machine, doesn't matter, but here's an IP address. Go run benchmarks on that, and it'll literally go run there too. And so we have this notion of a static machine. So it could be the machine that you're currently working on, it could be a machine across the room, or it could be a machine in the cloud. As long as it's addressable, it'll run the benchmarks on it. And then, universities like EPFL, they have something called Cloud Suite 3.0, which is one of the most commonly used suites for benchmarking and analyzing cloud, except it's missing this whole piece of being able to provision and handle all this really complex logic of, you hit the enter and it runs the benchmark and you get a result. For something like EPFL today, you have to go through pages of install documentation to get it to work. And it makes it harder to use. And so EPFL is even going to integrate their workloads into PerfKitBenchmarker. And so pretty soon you'll be able to get some of these other really interesting, well thought out sort of collections of benchmarks running in the cloud as well. And so our interest is to continue to evolve it. As patterns for developers change, we'll change too. If everybody stops running MongoDB, then we'll delete it from the benchmarker. So one of the premises we had for the benchmarker is it should be a living benchmark. And this is why we didn't go to an industry standards body or or a spec organization to get this done. We did this with the community so that we could change and evolve it over time with a given set of rules. And we're already starting to delete some benchmarks out of it, like Bonnie++ is going. We had a V1 of Mongo that wasn't as well configured as it could be. That's going. We have a better one that's using YCSB as the loader and looking at things like workload A and B, and so we continue to evolve it.
How do you measure the cost performance?
Price performance is an interesting one. We don't spit that out at the end. What you can do is you can look at your end-to-end runtime and the list of resources you used, and most providers have a cost calculator. You just plug the data in and you get a number as to how much it costs
It
you.
would be nice to, it's automatic, everything. Don't tell you how much.
One day? Price performance is a central tenet for us. Inside of Google, we can do price performance for Google Cloud Platform. And that's something we can do. We haven't put that out there yet. It isn't automatic enough, and the scoring is incomplete and stuff like that. So once we have that flushed out, we'll do it. The other thing we don't do at Google either is when we open source projects at Google, if we don't actually think they're valuable, guess what? We don't open source them. It's bizarre. You'd think we'd really open source our old crappy stuff to really confuse everybody. No, that's not actual Google. We actually go out there and we tell you amazing stuff and start whole new industries. Like the Hadoop industry actually started from a paper about MapReduce written by Google, back in 2006, and it created this whole new industry, which is pretty cool. And then we wind up at this later point, competing with open source technologies with the cloud things that we're providing, like Cloud Bigtable is a key value pair store that we put out recently, which is basically like a Hadoop HBase interface. And so here you have something that we grew up internally based on the same things that we wrote in the white papers, and now you have the open source software and comparing head to head. This is one where actually Google did better because we continue to evolve it from that point. And it looks pretty interesting. There are white papers out there for it. The analytics tool. This is an example of the analytics that you can get out of the dashboarding tool. Super simple. You basically come in here, you can configure your graphs, tell it what data to look at. You can click on a graph, it pulls up SQL, basically a SQL language. You can edit SQL directly. You can use a query builder tool in the query. The Explorer tool that we put out in open source is pretty powerful. And then you can take dashboarding links and you can send it around, put it in bug reports, share with management and friends, and we'll say, hey, look how cool this feature is that I built. And the dashboarding tool lets you do all of that. But how do we build it? We actually built the dashboarding tool. So the benchmarking tool is all written in Python. That was pretty portable across different platforms and languages, including Windows. But the Explorer tool we built using sets of cloud technologies. The analytics tool, PerfKit Explorer, started out as a serious sample for the industry on how to build dashboarding, dashboarding tools. And the way we built it is we built it using Google Cloud Data Store, Google Cloud Storage, App Engine, which is the platform as a service thing that automatically scales up and scales down your application. And at the heart of it was Google BigQuery. And so what we did is we looked at our cloud offerings that we had. We looked at the technologies that we had internally. And a couple of years ago when we built this tool, we said, let's build it all on cloud. And let's build it on Google Cloud. And it had some growing pains in the beginning. And then now where cloud is now, things are super smooth and very, very powerful. But this was an example of where I was saying things like, MapReduce in 2004 was like a seminal paper that we put out. And then out of this came like the Hadoop industry. If you look at Dremel, Dremel was another one of these papers where we talked about how do you do massively parallel queries at scale. That was the whole Dremel technology that led to things like Spark and all kinds of other technologies in the industry. BigQuery. Since this is so central, I'll give you an idea of why we built a analytics tool on top of BigQuery. And it turns out that a lot of customers build Internet of Things type applications on top of BigQuery for analytics. Power companies love this. They stream in telemetry from all their different power meters, millions of power meters, goes into a single, table in a database, and then they can query this thing out at amazing rates. And so BigQuery, what is very nice about it is it is a semi-structured data store. So typically when you write database applications, you create multiple tables, you have, foreign key, primary key relationships, you have, basically classic sort of schema. On something like BigQuery, you say, forget it, just stuff it all into one giant table, and it's fast. And how fast is it? It's super fast. It has, primitives like, hey, give me the average of all these values across, the database. We can do things like complex things like regular expressions. This is the semi-structured nature. You can take a single field in BigQuery and actually, basically create, key value pair relationships in that field and then pull them out through regex expressions. Super cool and powerful. And we did it because of this. So in PerfKitBenchmarker, we generate something like 10 billion, rows per month of data on, measuring the cloud. But here you can see an example of Google BigQuery where it's got, 10.5 trillion rows. Not billion, trillion rows. And it has, something like 38 petabytes of data is sort of the biggest customer, but here's an example. So if you have these, 100 billion rows in a query, which by the way is already like way out there in terms of size, 100 billion rows, you run a query like this, which is complex, right? You can see all types of computation is happening in this query, right? You go run it, you can run it over 100 billion rows in 11 seconds. You hit enter, and in 11 seconds, it's gone through every single row, everywhere, run complex expressions like these regexes, 100 billion of these regex computations, and literally come out with this set of results that come out of this. And, yes, you could go host and manage something like this yourself, based on top of Hadoop type, data queries. But BigQuery is something you don't have to manage. You stick rows in and you can get massively scalable queries out. And it shows you some of the dimensions there. Why does it work so fast? And this was, as we were looking at building our application, we're like, why is this so fast? Turns out a couple decisions. Google talked about columnar data years ago. Classic databases store rows continuously. Google actually stores each individual field of the particular row in a separate file, and this is called columnar data. So instead of storing one row, we store each field in its own table, row by row by row. This allows you to do things like massively parallel computation, where you can pass it down these fan-out trees, which I was talking about, like with the old benchmark. You can partition horizontally and vertically and pass it down to leaf nodes and say, leaf nodes, go find this data for me. They all compute simultaneously, and then they just aggregate the results back up, and out pops super fast results. So the benchmarker, the way we actually built this whole end-to-end system inside of Google for us is, first we started with the PerfKitBenchmarker, which is open source. This generates the data. This goes out, runs a benchmark in an environment with a given configuration, and it publishes the data to a backend data store. For us, it goes to Google Cloud Storage. We could write, and the open source tool actually writes directly to BigQuery. At the time we did it, we had so many different things running in parallel. BigQuery couldn't consume all these individual writers simultaneously. They now have a streaming API, which now can do it. But what we did is we wrote to Google Cloud Storage. It's an object store. We wrote the data, and then we had an App Engine app which would go in, take the data out, and put it into BigQuery. And out of this comes our analytics. And so one of the things that you can do, obviously you can go from BigQuery, you can put it into a spreadsheet, you can go directly to the BigQuery interface and you can query, or you can go take the analytics dashboards which understand BigQuery and create dashboards on top of this data. And so with that, hopefully I have given you a lot to think about in terms of cloud performance and analytics, and hopefully you will download at least the benchmarker, if not both the benchmark and the Explorer, and you now have a very powerful way to measure the cloud. So, thank you. Sure.
So when performance regression happens, how do you find what the root cause does that to help in that case?
So there's a couple of things that you can do. So the benchmarker tool, you're allowed to pass in metadata as part of the run. So first, the benchmarker tool collects a bunch of different data about what ran, where it ran, how it ran, what zone, what machine type, what version of the operating system were you running. It collects all that data already, and it stores that with the result. But you as the user can add extra metadata in here as well for whatever specific environment or config. When that gets published to the BigQuery database, we can mine out these individual fields, and what we have, and we're about to open source this, we haven't put it out there yet, is we have a alerting tool that literally sits there and mines the data in BigQuery, and every hour it'll go run a set of BigQuery queries and say, hey, if this data changes, send me an email. And so what you can do is you can do this on different metadata tags or the predefined metadata for every benchmark result. And one of the other things we've done is we've done advanced collection now with tools like dstat. We don't have it integrated with Windows yet, but on Windows we'd use xperf, but on Linux we use dstat. Dstat collects everything that's going on inside the guest, collects it as a log, and will also store that with your result. And so if you ever see an aberrant result, you're like, what happened here? You can actually go in and say, oh, here's the log, here's the dstat, and you can start the debugging process. Yeah. Sure.
Probably a simple question, but how do you determine if it is a hardware failure or a regression point? If something happens.
Cloud is complex. There are many, many layers in cloud between you, the user, and the resource that you're using, no matter what it is. If it's a database, on the back end, or a virtual machine, or you're sending to like data store. It can be challenging to figure it out. For us, for benchmarking, I can't say we have fantastic error handling on that end. If errors happen creating or deleting resources, we retry the operations for the benchmarks. If in the middle of running the benchmark there's a failure, it'll be detected and we just won't report the result. And so for us, we didn't try to solve the reliability problem. We figured cloud should just work, especially from the benchmarking end. And so we really focused our efforts to date around that. But you're right, there is more we could do around diagnostics. And hey, what happened to the cloud? And what's interesting about cloud is, if you had a benchmark failure, you can actually go to the service provider's alerts page and say, hey, is the service down or not, and collect that as part of your metadata. We don't do that yet, but definitely it's possible. Yep.
But there is no way to catch physical storage, like one drive is failed, or something like that.
Say that again?
So there is no way to catch, to know one physical drive under the cloud failed during that test.
Yeah, so the comment was there's no way to know if like a physical drive failed. Turns out there's actually no drives typically on the host where virtual machines run. So every cloud provider has a different way to do it, but when you attach a disk to a VM, that disk is actually a service that's running back to a backend service. And how that service is designed, it's designed to be redundant and resilient and multi-zone. And so if a failure of a single disk happens, you'll never know in cloud. Yeah. And so that's one of the things you just don't have to worry about there. Like for example, on Google, all data is encrypted at rest. So before data leaves a virtual machine in Google, it's encrypted before it goes to any storage backend. And so even if there are failures, and we have different types of mechanisms for you around like key and key management and ways to like protect your data like that, which is pretty interesting. We don't try to tackle that though with the performance benchmarking. It just happens transparently because that is the default. Data is secure by default. Sure. Any other questions? Oh, sure. Go ahead.
You provided a list of benchmarks in the presentation. The result is the mixture of them, or just you provide each result and the end user needs to analyze or interpret them?
So the question was, the statement was, hey, it looks like you provide all these different benchmarks. What do we do as the end user? Do we have to interpret all the individual results, or do you provide like an aggregated result? We don't give you a single result at the end, not yet. This is where I'm trying to get academia to come in and really think about like, how do you combine a result from like AeroSpike, which is a key value pair, NoSQL system, with something like a traditional copy throughput. You could do things like, oh, we'll take a geometric mean and we'll combine them, and we'll create a single uniform normal distribution and take a square root and give you a value. We could do that. That is definitely possible. Typically though, when you're looking at it as a developer evaluating cloud, you do want the individual results. So for us, all the individual results come out. They can come out either in a text form or JSON, and it comes out in JSON so that you can take the blob and import it wherever you want. Or you can tell it also to export it to BigQuery, and then just go write queries over the final results. It depends on how you want to use it though. And included in that is all the metadata.
And you told us that the preparation, cleanup, the provisioning, those are important. So you evaluate those values as an independent.
It is actually one of the results that come out. So for something like HPCC, classically the only result that would be reported out of HPL would be a gigaflops per second result. It'd be a gigaflops result. Or a that's it. You get, how many gigaflops are you getting? What we give you out of the benchmarker is we give you the gigaflops result that was produced, We give you how long did it take to provision, how long did it take to tear down, and how long did it take to run this thing end to end. And all of these come out as individual results at the end, which starts to explain how we get 10 billion of these results per month that we actually generate ourselves. Some people have asked us, hey, if you're already running all these benchmarks on Google Cloud Platform, can you just give us the data rather than us having to run it? Yes, I can. If you call me, I'll give you all kinds of data. At some point, we'll probably create a reference set. We've been talking to different universities and different cloud benchmarking companies like Cloud Harmony to host a reference data set, and actually trying to do it for multiple clouds. And so what I'd love to do is, I'd love for different cloud providers to give credits to some trusted entity, and then they can go create the set of results that we can all go look at and mine and do interesting results on. It will happen sometime this year, I suspect.
But again, how to set the reference scenario is a really difficult thing to do, right? So you say not only execution time, but also setup time is very important. But it's almost impossible to tell. Setup time is like a 50% important compared to execution time kind of stuff.
So let me tell you where things like provisioning time really matter. If I told you you could start 1,000 VMs in Google Cloud in less than 11 minutes, is that interesting? Versus, hey, I started 1,000 VMs. Oh, that's right, other clouds take like a half an hour to an hour to do this. And so this is where it becomes really interesting is the acquisition and provisioning of resources is something that you will adapt to as you create different applications in cloud. How long does it take to deploy my App Engine app? Or how long does it take to deploy my Heroku app or whatever it is important because if you have a service outage, you want to make sure you can roll that thing out fast, which is why we collect all these results. How important any one of these metrics is to you really depends on what you're benchmarking, what you're looking at. If you're not using NoSQL, none of these results from Aerospike, Cassandra, MongoDB, or Redis are going to be interesting. If you're using a classic database like SQL Server or MySQL, the results that come out of Sysbench OLTP are going to be more interesting. There's also something called Percona TPCC, which gives you like a pseudo TPCC type result. That may be something we add in the future if the community asks for it. If one of you actually wants to write that, I'd be happy to work with you to figure out how we integrate that. So each of these results really depends. And so other things we've been looking at for the benchmarker is doing things like grouping. So one of the things the benchmarker does is it creates sets. And so when you say benchmarks, -- benchmarks equals Google set, it'll run the set of benchmarks Google thinks is important. If you run the standard set, it's the set that the community has all agreed matter, including MIT and Stanford, who are the steering committee for the standard set. And then if you take something like a vertical, like, hey, I want to understand how does this look like for social applications? We're looking at now, how do we group these different benchmarks into these sets where it's like, hey, this is social, this is gaming, this is, traditional line of business application, and then you can tell the benchmarker, go run the representative set, and then you can go compare, each of the different cloud providers to get an idea as to what to expect for your own application. Because a common pattern for performance is to say, take my application, there are things that these do that look like your application, and then take the set of these to project what you think will happen with your app. And of course, running your own application is, the ultimate thing, but not many people have offered to check in their proprietary code to the benchmarker. So that's hard to get. I mean, that's very, very hard to get. But also automatable, by the way, through the benchmarker. Sure.
Is there a good way to compare performance between App Engine and GCP?
App Engine and what?
And Google Compute Engine platform?
Oh, yeah. Is there a way to compare like App Engine and Compute Engine?
Yeah.
We're looking, if you notice, there's a very suspicious important workload that's missing here, which is a web workload, which is the thing that you'll be able to use to compare against that. It's one we have identified. We had the issue opened up on GitHub saying, hey, we need a web workload. And people have recommended, oh, I want PHP bench, or I want Apache bench, or I want whatever other web benchmark. Haven't decided which one it is. But when we get there, we will definitely make it work, on GCE and on GAE, Google App Engine, so that you can literally go in and say which one compares. Google App Engine is a little different because it's meant to scale to millions and millions and millions of users simultaneously, whereas like a single VM won't ever handle that load. But you should be able to compare it. Sure. Yeah. Sorry.
I don't support like the Perf4 GPU. Is it supported?
So the question was GPU benchmarking. We don't have a GPU benchmark in here. Nobody submitted one yet. And what I don't know is, in the industry, is this still a more exotic, use of cloud or not? Different cloud providers provide GPUs to go do scientific computing and codes. What we found at Google is, with the proper CPUs, they can always outperform the GPUs. It's really interesting. There are things that GPUs can do really, really well, but with like Haswell supporting AVX2 with the SIMD instructions, it's like single, instruction, multiple data. It looks a lot like what GPUs can do. And so there's this sort of, race between GPUs and CPU capabilities, and they keep marching. And every time you think, oh, we should all go write, code to GPUs for specific applications, then a CPU comes out with a feature that's like, I didn't need to do it. And so we just haven't put one out there. If somebody had one, I'd be willing to put it out there. Yeah. So that's what it hasn't been the top thing that customers ask for. In fact, I haven't seen a single customer asking for a GPU yet. Doesn't mean they don't exist. It could just be self-selective because we don't offer GPUs at Google. But at the same time, it has never been something that's come up in in a sales discussion or a competitive discussion.
Actually, I met the kind of customer who went to AWS. Actually, I have an Azure, but he chose Amazon because they support the GPU. So I'm interested in whether the Google is going that way or they rise with the kind of PerfKit for the GPU.
Yeah, I can't say. I can't say one way or the other, like where the future roadmap is going. I will say, of course we've looked at all different, considerations, but yeah, where the future is, I have no idea. Yeah. Sure.
More analytics, tactics question than benchmark.
Okay.
You mentioned boosty behavior.
Yep.
So when you don't have context of why boosty behavior happening with the services, do you have a suggestion of how you can analyze those service performance when that happens? And you might be affected by the boosty behavior for your own performance.
Yeah, so the question is when you're getting this burst from the provider, whether it's on disk or CPU or whatever it is, or network, how do you know as a user you're getting it? Typically you don't. It's really interesting. I haven't seen anybody providing the analytics that like in the dashboards or the monitoring saying, hey, you're bursting right now. I think it would be a great idea. I think it would be valuable as a user, because that way if you're doing something like capacity planning, am I planning to the actual capacity, or am I just currently taking advantage of a benefit? And the only way you can mitigate that today is just to run for a long enough time that you'll get past any of these. And typically if you run more than a half an hour, anybody's burst is gone.
Yeah, but as you say, depending on day or time or week or month, it can be very different.
It can be very different. Typically networks are over provisioned. And so that's one that can change, up or down. CPUs can be over-provisioned. Google doesn't over-provision CPUs. It can happen on different providers. We don't do it. But it can be difficult, like seasonality. This is one of the reasons why most infrastructures run at like a 70% utilization. Most people don't provision and run at 100%. In cloud though, what's interesting is you could actually run at 100%. And if you hit this state where you're like, oh, I'm dropping request, you can spin up an additional resource pretty fast. And this is why the provisioning speed matters so much. If you can provision something in 10 seconds, you can adjust to this pretty fast. If it takes you an hour to provision it, well, that's not really going to help you. And this is why we include the provisioning time as part of these benchmarks.
Actually, do you think approach like this, or actually having toolkit like PerfKit could be useful to actually get insights to the situation?
Yeah, the PerfKit benchmarker will definitely give you insights. I mean, one of the things that we do, for example, for networking benchmarks, inside of Google, we run this thing, you know, we have all kinds of other monitoring. There's a difference between monitoring and benchmarking. Monitoring is, you don't know what you should be expecting, all you know is what's happening. Whereas benchmarking, you know exactly what you want to see, and you know the value you got. And so what we do for us is we run these benchmarks every hour, every half hour, every 5 minutes. Just depends on what it is. And so we get this very long trail of sample points. And over different periods of time and days and running them in parallel, like one of the cool things about cloud is you don't have to think serially. It's like, oh, I want to understand the network. Well, I need to run for an hour. Or you can run 1,000 machines for 5 minutes, right? And you can figure out this behavior. And so one of the things that we do is we run both things in parallel and collect these results regularly. And you start to get the statistical behavior. And so as a application developer, before you deploy your app, you're probably going to look at your load and do some load testing and monitoring and analyze it over a period of time. And then after 2 weeks, if you're really, really happy with this first V1 app, then you'll go release it, and then you'll find out you probably under-provisioned it anyway, and then you'll just add a bunch of resources. Yeah.
We'll get another situation.
Or the other situation where then you're looking around for a job. Yeah.
So are you thinking about perhaps PerfKit benchmark may actually also go more than those 2 slides on this benchmark, or actually more?
Do we think that we're going to take PerfKit Benchmarker to go do more than analyzing the cloud? Not currently, but it is an amazing teaching tool. Like if you've never used any of these cloud providers and you want to really see how it works, if you run the PerfKit Benchmarker, literally it's running line by line, telling you exactly what it's doing, including things like sudo apt-get install iperf. Sudo, it actually is taking you through both what's happening locally on your machine to provision the resources, but what's happening in each and every VM or resource that you're running. So you really could sit there with 2 windows. One window with the benchmarker running and the other window just copying what it's run and literally produce parallel results. And so from that end, it's really, really useful to see and compare what are the different clouds doing. Yeah. So, sure.
I noticed that in your slides that you have some sort of terms like reference and refs, and I was wondering about the visualization aspect of that output.
Oh yeah, so if you look at this, what's really cool about this tool, this is the PerfKit Explorer. This is all open source. It's written in Angular and a little bit of Clojure. It's not very tightly integrated with the Google Cloud Services other than it's running on App Engine. But the visualization aspect of the dashboard is all GViz. So GViz is a componentized set of widgets that you can use to build cloud applications. And GViz has all kinds of charting and graphic capabilities. And I didn't even show the cool ones here where you could get like maps and like geolocate points on maps and all kinds of stuff you can do with GViz. If you just go to Google and type in GViz, you'll see like the API, and it's just, you basically pass JSON to the back end, and it gives you back a graphic, and then you get cool graphs and charts in your internet applications. And so that's how we built this one. Yeah. Sure.
One more question.
Okay. Sure. Yes, you. Right there. Sorry, in the white shirt. Yeah. Sorry. I know it often looks like I'm looking like one person over.
So this might be more a marketing question, but I think cloud makes a lot of things possible, but I think different companies need different things. So do you change the way of promoting Google Google Cloud to different companies, especially depending on the size of the company or the industry of the company or something?
So say that again. So
do you change the way of promoting Google.com? For example, you can do blah blah blah, depending on the size of the company or the industry.
So the question was more of a marketing question. Remember, I'm a developer,
Yeah.
so it's always dangerous to ask me these marketing questions, but I will answer because I spend a lot of time, with sales and doing things like blog posts. The question was, do we change the way we talk about, cloud with different customers and how it's sold? Yeah, most definitely. I think it has to be specific to the individual. But if you go to something like cloud. Okay. Let's see if the internet is with me today. Let me show you something.
Yeah,
interesting. because I think this almost directly addresses your question. And hopefully it doesn't pull up Japanese, otherwise one of you is going to have to help me. So if you go to like cloud.google.com, one of the things that you'll see each of the different cloud providers doing, if we're connected to the internet here, you'll see that they actually talk about different market segmentation. Like, this is kind of cool down here, where it says something like, hey, top cloud, products that build on cloud, use these types of services. But if you're a gaming company, and you click here on gaming, here are the types of things that you typically see. And what's interesting with this one is you see, oh, you typically have some sort of API because you're coming from a mobile phone or some sort of desktop, and you're interacting with the back-end game engine. And what games do, you may not know this, things like Candy Crush make like $600 million a year. How do they do this? What they do is they send all of these analytics back to something like Google Cloud Storage and Data Store, and then they run really complex analytics on top of BigQuery, and they find out, you really like the blue crystal, but Kenji likes the pink crystals. So if we put more pink crystals, I'm doing that on purpose, he has girls. So if you put the pink crystals on Kenji's screen, Kenji seems to buy more extra add-ons than if he's just saying, blue crystals. And so these companies are literally collecting all this data, and then they figure out exactly what to market and offer back as like add-ins and upsells. So this is one, right? So here's like, oh, here's what that company might do. If you're building mobile applications, like a different type of mobile application, here are the things that you'll typically use as part of cloud services. Phones don't exist without a backend. This is the amazing thing. Mobile has grown by leaps and bounds, but it doesn't exist without the backend. And everybody has a backend somewhere. So it doesn't just stop at the app. And then something like Hadoop is how do you do mining of big data? And here you use like something like Compute Engine is taking the data, storing it into Google Cloud Storage. You're running the Hadoop analytics. We have sets of libraries that we put in open source for making Hadoop run better on Google Cloud. And then you can run these parallel computations. And then this is kind of what the workers are doing at the backend VMs. And so does the approach change with different verticals? Sure it does. Does that answer the question? Sure.
Yeah, I have another question. So, do you have any specific idea about what especially startup company needs for cloud or is looking for when they choose cloud?
The question was, do I know what startup companies typically want in terms of choosing a cloud provider? Yeah, they want inexpensive, and this is one of the reasons why startups all go to cloud. It used to be, could you imagine a company of 12 people making $1 billion company? That never happened before. And so when you look in the industry and you see, companies like Instagram, the only way they were able to do this was because cloud was there. And so one of the things that Google did, and this is where it's really differentiated, you can go check it out, don't take my word for it, but go look you can Google it if you work for Microsoft, I guess you can, is it Ring It, Ching It? What's that thing called?
Bing it.
Oh, Bing. Oh, sorry, Bing it. I just joke here. You could Bing it. You could actually go to Bing and run this. But we at Google have been doing two things. One is we were the first group to go to minute billing. So when you start a VM, you pay for 10 minutes and then every minute afterwards. That was pretty cool. Nobody else does this yet. And so if you start a VM, you use it for 10 minutes and turn it down. At Google, you pay for 10 minutes. Everybody else, you pay for the full hour. And so instantly already for like a dev test environment, it's much cheaper because you get this incremental billing. The other thing Google did that's pretty unique that nobody else does yet either is the more you use Google Cloud, in particular VMs, the cheaper it gets. So if you run a VM for a whole month, we automatically discount 30%. Did you hear what I said? If you run it for the whole month, we just gave you 30%. On other cloud providers, if you want to get a discount like that, you have to commit to a year commitment or 3-year commitment. You have to give them a bag of money up front to get cheaper prices. On Google, we just give it to you. It's like, oh, you ran it for the whole month? Okay, yay, it's cheaper. And so we do this, we do this differentiated billing. But the third thing we did, and actually you saw a price announcement by another cloud provider just today, in response to something we've been doing at Google, which is, if you go look up, we jokingly call this Moore's Law. So everyone's heard of Moore's Law. Moore's Law is, the doubling of CPU speeds every 2 years, which is Moore's Law. if you go up, or we jokingly call this Orr's Law, because Orr's is the head of technical infrastructure at Google. He was number 8 employee and so forth. But he has been driving this thing of Google Cloud pricing ought to inversely follow the power of CPUs, meaning every 2 years, CPUs get faster, and every 2 years, cloud should be half the cost. And so the cost should be continuously getting driven down and driven down and driven down and driven down over time. And so if you look, last month we announced a bunch of price cuts, almost like 15 to 20%. If you look a couple months before that, we did the same thing, and a couple months before that, we did the same thing. And so there's this continuous, drive to push down the prices because computation is getting both faster and cheaper. And so we're trying to drive that down to the customers. And I know that's a very marketing answer from a dev, but you asked me, and so I answered it. Yeah. Okay. All right, thanks. And I'll be around for a few minutes.
Okay, so we have this room until 9:30, and it is around 8:50, so we have 40 minutes to mingle, do networking, ask more questions personally. And also, we still have good amount of food, so please don't hesitate to get some.
Cool. Thank you.
Okay, one last thing.